Okay, dear students, welcome to this video. And in this video, we are going to learn everything about the Kepler's laws of planetary motion. This is a new topic added into the new syllabus, I mean to say, and that is why it should be of the prime importance, and IB should be interested in it. In the last syllabus, Kepler's law was not there; it was not covered. Okay, let's see what are the Kepler's law. So these two, the first laws, they came into existence in the year of 1609, and the third law came into existence in 1618. And just to make the picture clear, the law of gravitation was given by Newton in the year 1675. Okay, so this is the whole picture, and Kepler is preceding Newton. We can say that. Okay, now the first law is every planet moves around the sun in an elliptical orbit with sun at one of its foci. So to understand what is this written here, we must know what is an ellipse. So this is basically an ellipse, like this is a circle, okay, and it has only one center. So when it starts becoming having a little bit bulge at the central part, so it starts becoming like this, and at that time we call it ellipse. Now the ellipse is not having one center, ellipse is having two centers. It means like when you are stretching the circle and you're converting into ellipse, the same center is converted into two different centers, which are not known as center obviously, but they are known as foci. There are two foci, okay, and this is what is ellipse. Couple of more things in ellipse. This axis, which is kind of the longer one, it is known as major axis, okay, and this axis, which is perpendicular to the major axis, this is called minor axis because it is shorter in length. This is minor axis, the other one is the major axis. Okay, we would be doing these things in detail in this diagram. I will be telling you these things again, but just because like I want to clear the picture what is going to happen here, that is why I've given you very elementary knowledge about ellipse. This is ellipse. Now we read it again. Every planet moves around the sun. You see, in those years, like there was a notion that earth is flat and sun is moving around the earth, and all those kind of notions were they used to exist at that time. So Kepler was the first person. He has to tell people that yes, sun is at the center of the solar system and planets are moving around the sun. So that was first surprising element in his theory. The next thing is that they are not in circular motion, they all are in elliptical path. Okay, so this is an elliptical path. In this regard, I can tell you one more fun fact. Like in the case of Earth, the orbit of the Earth is approximately a circle. The length of the major axis is approximately equal to the minor axis. It is just a short of kind of like 30 kilometers or something. So they are almost equal to each other. Technically, the orbit is still an ellipse, but we can still say like only in the case of Earth it can be regarded as a circle. Why? Because it is almost equal on the major axis and the minor axis. So that is I would say a special fact in regards to Earth. Okay, so this is the first law. Let us move to the second law. Kepler's second law is the law of area, which is very, very important to understand. Listen to this. What is happening is now we want to comment on the velocity or the speed at which the planet is moving in the orbit. So your question should be, is that constant? Well, the answer is no, it is not constant. It is a variable. So what happens is, like, let's say this is an ellipse and sun is occupying one foci. The other foci is mathematically present there, but there is no astronomical body which is at that point. So this foci here, F2, I can say there is nobody there, it's empty, but the F1 is having sun at its location. Okay, and the planet is moving around the sun in an elliptical manner, just like this. So this is the sun, and all planets are moving like this. You can take the example of Saturn, you take the example of, like other elements, other planets. So that will be more elliptical. Okay, so this planet is moving like this. Now, what he says is that when the planet is moving and the line which is joining the center of the sun with the center of the planet, you can say the position vector of the planet with respect to the center of the sun is sweeping the same amount of area in same time duration. It means that it is going from this to this, so this area can never change. Like if this is the area that was swept in 6 months of the traveling, so in every 6 months, wherever the planet is, it would be sweeping the same amount of area. Like when it is near to it, so you can clearly see that this area will be swept, and this area is actually equal to this area. But as we can clearly see here, the length of the position vector is lesser, smaller, so it is traveling a bigger distance. So the distance between A and B and the distance between C and D, we clearly see that the distance A and B is much larger than C and D. Clearly the velocity is higher, or the speed, we can say, to be more exact, speed is higher when the planet is at lesser distance away from the sun. Okay, so this speed is more, here the speed is lesser, and accordingly you can create as many areas as you want, but this area in the time period of 6 months has to be equal every time. Okay, what else I can tell you here? This point, the nearest point to the sun, it is given a name, perihelion. Perihelion is the point which is near to the sun, and the point which is away from the sun is called aphelion. Aphelion. Aphelion is the word. It is many times known as apogee also. Apogee, and this is known as perigee, and some books are writing it as perihelion and aphelion. Accordingly, you can take the terms. This is the law for the velocity. So this is Kepler's law of area. Yes. Now we are moving to the Kepler's third law. Now Kepler's third law says that if we are talking about the time period now, like not the velocity or the speed, we are now considering the time period. So the motion which is taking place here, and we want to find the time. This time square is found to be directly proportional to a cube. What is this a? See, this is the major axis. This a is known as semi-major axis. This a is known as semi-major axis. So it is 50% of the major axis. That is why we call it semi-major. And this b is called semi-minor. Semi-minor, you can say. So this is B, this is semi-major axis, this is A. So A is basically the, you can say, the average of the two radiuses and all that. Anyways, two radius, which radius? This is the R1 and this is the R2. Okay, from the center of the sun, and you take the average, so that will be equal to A. So T square is directly proportional to A cube, that is semi-major axis. This is the law for the Kepler's third law. The square of the period of the revolution is directly proportional to the cube of the semi-major axis of the orbit. I hope things are pretty clear. Now, this law, it is applicable on two different planets. Like there is one planet which is moving here, and there is another planet which is moving in this orbit. You can clearly apply this, and you can say t1 divided by t2 square is equal to a1 divided by a2 cube. And this is a really important formula, really important concept for you, because in every other time you are going to get this question. Kepler's is a new topic added into the syllabus, and as per all the questions that I can see, this topic is going to be very important for your exam, and Kepler's third law is going to be utmost important. Okay, dear students, so this is Professor Varun. Thanks for watching the video. This is Kepler's law for you. We would be now moving into the satellite motion. All the best. Bye.